Hi everyone, welcome to this talk on online map inference for determinantal point processes. So what is a determinantal point process? So suppose you are given a bunch of points v1 through vn in Rd, and let's say you have a parameter k. A determinantal point process is a way of sampling k subsets of these points with the property that the probability that you choose a particular k subset is proportional to the volume of the simplex formed by these k points. Okay, so nearly orthogonal points have a much higher probability of being chosen than let's say points that are along the same direction. Okay, so a KDPP is a way of sampling that promotes selecting diverse subsets. Okay, so it has a bunch of applications. So we are interested in the problem of max a posteriori estimation or map estimation in DPPs. And so the problem is basically to find a subset S of size k that has the largest probability of being sampled. Okay, so effectively, this is a question of volume maximization, and so this problem has a lot of efficient algorithms. It's well studied, and there are actually very simple practical algorithms which are based on like local search procedures that do well for this problem. So in particular, we are interested in the streaming and the online versions of these problems where the points v1 through vn arrive one by one, and we don't have the space to store all of these points. Okay. And our goal is to consider this streaming setting and build core sets in this streaming setting. Okay, so what is a core set? An alpha approximate core set for KDPP is it's basically a subset of these points with the property informally that solving the problem on the core set is equivalent to solving the problem on the entire set of points. Okay. And now our goal is that these points arrive one by one, and we want to build a core set on the fly. Okay. So this sort of a thing is known in the streaming setting where you're allowed to update the core set as new points come along. But we consider a very restrictive model called the online model, which has a bunch of applications where every time a point arrives, you've got to decide whether to keep that point in the core set or not. Okay, so it's like you decide once and for all whether to pay for that point. If so, you keep it and move ahead. Okay. Now the goal is to, of course, pick a small number of points overall and still get a good approximation. Okay. So we show two main algorithmic results. So first, what we show is that the offline algorithm of local search can actually be modified into an online setting. And the caveat is that it needs an additional stash, which turns out to be important. So instead of when you update the solution, instead of throwing away a point that you remove, you store it into a stash, and the point can come back again. Okay. So by using such an algorithm, we can show that you get the same approximation guarantee as the offline algorithm, but the space complexity depends logarithmically on a certain condition number parameter. Okay, so we show that in practice, this algorithm is actually pretty good, but it turns out that in theory, this can be as bad as linear. Okay. So to overcome this, we present our main contribution, which is an algorithm that has an additive error parameter. Okay. And what we show is that we can achieve a number of columns or a space complexity that is independent of the total number of columns, completely independent of n, provably, and you get an approximation factor that is almost k to the k, which is what the offline algorithms also achieve, but with a slightly additional term which depends on this additive error. And our main contributions here are to kind of evaluate these algorithms in experiments and study the complexity of this online question. So thank you very much.